Okay, today we talk about section 3.5, and in this section, knowing your parent functions is going to be very important. So if you already have those done, that's great, and if not, let's get them done by the end of this section, okay? Because in this section, we're going to talk about transforming them. So this is transformations. Of functions. So let's start with a basic example. Here's one of our parent functions. Let's say f of x is equal to x cubed. Okay. So if we use a basic table, if we let x equal just some numbers right around 0, so we can get an easy understanding of what's happening, then f of x is negative 2 cubed, which will be equal to negative 8. Negative 1 cubed is equal to negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. Okay. Now, I already know the shape of this function. Okay? So for nice, neat graphing, I'm going to draw the shape of the function in as I know it, okay, and then label it with the appropriate points. I know this is 0, 0. We'll say this is 1, 1. And this is 2, 8. Okay, we've labeled it by making it true by labeling it. Okay, so this is negative 1, negative 1. And down here will be negative 2, negative 8. Okay, so this is the shape of x cubed. Now, we could look at a different shape, or a different function, a different function, and it will have the same shape. Okay? Let's look at f of x, which is equal to x cubed plus 2. Let's call it g of x so we don't get confused. Okay? Then over here, g of x is negative 2 cubed, which is negative 8, but then we're going to add 2, so it's negative 6. Okay? At negative 1, we have negative 1 cubed, which is negative 1, and we add 2, which is now 1. 0 cubed is 0 plus 2. 1 cubed is 1 plus 2 is 3. 2 cubed is 8 plus 2 is 10. So notice what happened here is the x values stayed the same because I picked the same, but each of the y values, or the function values, I added 2. So what that's done then is that the shape will stay the same, but every y value gets shifted up 2 units. So this is the point 0, 2, and this is the point 1, 3, and 2 is way up here, 2, 10. Here we have negative 1, 1, and here we have negative 2, negative 6. Okay. So notice these are not to scale. Okay. I just labeled them to make it true. We could also consider another function, h of x, which is x cubed minus 1. If we do that, we have negative 2 cubed, which is negative 8, and then we subtract 1 to get negative 9. Negative 1 cubed, which is negative 1, and then we're going to subtract 1, which is negative 2. 0 cubed, which is 0, minus 1, which is minus 1. 1 cubed minus 1 is 0, and 2 cubed, which is 8, minus 1, which is 7. So now our y-intercept is at 0, negative 1, and the graph will look like so. It should have the same shape. Okay. Now I'm going to label this to make it true. So this is 0, negative 1. and at 1, at 1 we have 0. Okay, so that needs to be there. Okay, so we don't have to be great artists, but we do have to label to make it appropriate. And at 2 we have 7. And down here we'll say this is -1, -2, and -2, comma, -9. Okay. So these all need to have the same shape. Okay. And that's why we will label it to make it true, to make up for our artistic abilities. That's fine. Okay. The important thing to understand is that, again, the x values stayed the same because I picked the same ones, and the only thing that happened is that I changed the y values. And so what that did was drop the shape, okay, specifically 1 unit. Okay. So now in general, let's make a rule that you can see here then. Okay. So in general, for any function, if we have some function y that's equal to a parent function, f of x, or a basic function, whatever you want to call it, and we add some constant, what will happen then is it's going to move the function up or down. Okay? So this provides a vertical shift. And so up or down has to do with really the value of the constant. We're going to go up if k is greater than 0, that is if it's positive. Okay, so that means we'd be adding. And we'll go down if k is less than 0. So in other words, we'd be subtracting that constant. Okay, because adding a negative is the same as subtracting. Okay? So that's what we'll worry about for adding a constant outside of the basic parent function. Now it will happen differently if, say, our function looked like this. So again, let's work with f of x is equal to x cubed. It has the basic shape like this. This is 0, 0. This is f of x. But say I didn't want to translate this function up or down. Let's say I wanted to move it to the left. Okay. So let's say I move it to the left, something like this. But if I maintain the shape, I'm wondering what happened here. Okay. And let's say I moved it 2 units. So this is -2, 0. Okay. What is the function that happens here? Well, notice what happened is that the y value stayed the same, but I changed the x value. Okay. So the resulting function that comes from this is that x is equal to, now what we will have changed is we're changing what happens with the x, and then the function's still going to be cubed. Okay. Because we need to have that same shape. We'll fill this in just a minute. Now, let's say I moved it all the way out here, our center point, from 0, 0 to 4, 0, but we keep the same shape. And actually, I should call this a g of x, shouldn't I? Because we're a different function, and then let's call this an h of x. Now, because we have the same shape, it will be something cubed, but I'm moving the x values. So I want to make sure that what I changed affects inside of here. Okay, so we want x to be 4 when the function is 0. So what do we have to do? So if I had x plus some constant inside of here, and it's cubed, we want to know when that's equal to 0. Okay. So if I take the cube root of both sides, we'll get x plus k is still equal to 0. And so what we find out is that x must be equal to negative k. How is that helpful for us? Okay, well, in this case, we know that when y is 0, x was equal to 4. Sorry, you guys. Let's see if I can get this to autofocus better. There, okay. So when the function is 0, x was equal to 4, so 4 will be equal to negative k. Or if we solve for k, we see that k must be minus 4. And that is what we put in up here. This is the function x minus 4 cubed. Okay. Let's try the same trick with over here and finding out what we should do. So if we set the function equal to 0, we get x plus k is equal to 0, so x is equal to negative k. That is still the same. But now it's a different function. So what happens? Well, x is negative 2, so we want to know when negative 2 is equal to negative k, and that's when k is equal to 2, and let's emphasize the fact that it's positive. So what that means then is that this is the function x plus 2 cubed. So what that means in general then is, let's say we have some function, y is equal to a function, but now we've changed the x value inside that parent function. In this one we just used x cubed. Okay. This will provide a horizontal shift. And here's what's counterintuitive about this, is if k is greater than 0, then that means we're going left. If k is less than 0, that means that we are going right. So here, k was less than 0, so we were subtracting 4, and we subtracted 4, we moved to the right. Here, k was positive, so that means we were adding 2, but we actually moved left. So there's an acronym that I like to have that helps me with this. It's LARS, it's the name LARS. And what that means is that if we're going left, we need to be adding, and if we are going right, we are subtracting. So that will help us. This is a key that I use every single time when I'm doing a translation. Okay, so those are the horizontal and vertical translations. We also have a reflection. Okay, so for example, if our, again working with our basics function, f of x is equal to x cubed, this is 0, 0, this is 1, 1, this is 2, 8, this is negative 1, negative 1, and this is negative 2, negative 8. This is f of x. All right. Now what happens if we look at this? What happens if we if we had g of x that was equal to negative x cubed. Well, if we look at that, then as we plug it in, the only thing, here's our x cubed values, the only thing we have to do for g of x is then make the original function values negative. So this becomes positive 8, positive 1, negative 0 is still 0, this one becomes negative 1, and this one becomes negative 8. So that is, here at 2, 8, I now need 2, negative 8, which will be down here. At 1, instead of 1, 1, I have 1, negative 1, which will be here. At 0, 0, it'll stay the same. So for every value of y, I'm changing the sign. So this side of the function reflects over this. Now on the left-hand side, instead of negative 1, negative 1, I'll have negative 1, positive 1. Instead of negative 2, negative 8, I'll have negative 2, positive 8. And the same for all these values in between. I'm going to make those values negative, which will cause a reflection. So this is y is equal to, or g of x is equal to negative x cubed. So in general, if we have some y that's equal to the negative of our parent function, what this will do is provide a vertical reflection. Okay, reflection is also a flip of the graph. That is, we flipped it over the x-axis. So this is going to make graphing things and sketching the graph of our functions so much easier for us. So let's do some examples so you can see. Okay. Let's say, for example, that let's say our basic function y, which is equal to our f of x, will be the square root of x. Okay. So the square root of x looks like this. This is the point 0, comma 0. Okay. Then we also have the point 1, comma 1, and 4, comma 2, etc., etc., etc. So this is the square root of x. Okay. And the function we are given is that we're going to take y, we're going to modify our function by adding 2 to the x, and then subtracting 3. Okay. This is our modification. Now in terms of the actual function that we're given, what that looks like then is that wherever I see the x, I need x plus 2, and then when I'm finished, then I can subtract the 3. Okay. So notice that that 3 is not underneath the radical. So we have to realize what each of these things are going to do. And if I'm going to add 2 inside the x, here's where I'll use the Lars to figure out if I'm going left or right. Well, I'm adding, so that means I have to be going left. Right? So this will give me left 2 units. And here we're adding the constant. In this case, we're adding a negative 3 or subtracting 3, so that means we're moving down 3 units. So now let's keep track of our main point here, which is the 0, 0. Okay. This is the main point because originally we can read the domain from here. We can read the domain as 0 included to infinity of our basic function. Okay. So as I'm moving here, I can move to the left 2 units. Okay. This would just be the square root of x plus 2. Okay. Basic shape. And it would have the point negative 2 comma 0. But I need to also drop it 3 units. Okay. So I can take this point and now drop it 3 units, label it to make it true, okay. And then I can draw in the basic shape. Now this is just a sketch, it's not an exact graph, but by just knowing the sketch, notice now I can answer a lot of things about this function that I couldn't before. Like, for example, I could ask you what the domain of this function is, and once you sketch the graph, you can see now that the domain starts at negative 2 and goes to infinity. On the other hand, the range, if I asked you about that, the lowest value of y is negative 3, and then it will continue on to infinity. So previous to translations, answering questions about domain and range for this may have been much more difficult. Okay, let's do another one. Let's say our y is equal to a parent function f of x that is the absolute value of x. So the absolute value of x looks like so. Okay, it's our v-shaped. And now let's change it. So we're going to change the parent function by making it negative. And let's subtract 3 from the x and add 4. That'll give us a lot of work there to do. And in terms of our parent function, then that means we have the negative absolute value of x minus 3 plus 4. So let's see if we can do this all at once. Okay. So this is going to make us go up 4 units. Here I'm subtracting. So that means I have to be going right, okay, 3 units. And this negative will provide the reflection. Okay, so if we reflect this over, it's going to go the opposite way. So let's do some moving so we can do this all at once. I need to go to the right 3 units. So 1, 2, 3, and then up 4. So this is the point 3, comma 4. We'll label it to make it true. And if there wasn't a reflection, I would just draw the V in there. But I've got a reflection. And actually this point should be up a little bit higher. Well, it's just a sketch, so we'll be okay. All right. Let me move this up just a little bit higher. We said that's 3, comma 4. Let's move it up here, because this would be the point 3, comma 3 on the absolute value. So now it would look like this: 3, comma 4, like so. Okay. So as a sketch, then we could answer questions about domain and range. Right? We could say, what's the domain of this graph? And the absolute value has a domain that's all real numbers, and so does this translation. On the other hand, now, the range used to go from 0 to infinity, but with the reflection now in blue, the lowest value y can take on is negative infinity, and it will go all the way up to 4, the function value, and that is included. So that's how you can use sketching to help you answer some very basic questions about domain and range and get a very clear idea of what's happening. Now these aren't the only types of transformations. We can also stretch or shrink. Okay. Functions. So to do this, let's look again at, let's let f of x be equal to the square root of x. Okay? So it will look like so. Giving myself enough room here. This will be 1, comma 1. This is 0, comma 0. And this is 4, comma 2. This is the square root of x. Okay. So what if we have g of x that is now 2 times the square root of x? Well, at 0, we get the square root of 0 times 2, which is just 0, and so it stays the same. At 1, we'd have the square root of 1 times 2, which is 2. So we'd have 1, comma 2. At 4, we have the square root of 4, which is 2, times 2, which is 4. So now the graph looks like this. And I guess we should make note of the domain here. Again, our domain goes from 0 to infinity, and our range goes also from 0 to infinity. In this case, the domain and range has not changed. The domain here is still 0 to infinity, and the range is still 0 to infinity. Okay, we've not moved up or down. The difference is that I've pulled this graph up, I've stretched it, and so it's going to this concept of infinity, but it's going to go there twice as fast. So therefore we say it's been stretched. If we look on the other hand at h of x, which is equal to 1/2 of the square root of x, when x is 0, we get the square root of 0, which is 0, times 1/2, which is still 0. So they all three meet in this place. At 1, we have the square root of 1, which is 1, times 1/2. So this is down here, 1, comma 1/2. If x is 4, we get the square root of 4, which is 2. 2 times 1/2 is 1. So now we get 0.4, comma 1. And if we note again, the domain has not changed. It goes from 0 to infinity. Notice the range has not changed as well. It's also 0 to infinity. So this range will go to infinity, but notice that it's going to do it slower, in fact, half as slow as the square root of x. So in this way we talk about a shrinking. So in general what that means is that if we have y is equal to a times some f of x, or a constant, however you want to say it, you're going to get a vertical stretch if a is greater than 1. Okay, so here a was greater than 1, 2 times the x, and we stretched it. Okay. Now if a is less than 1 but greater than 0, okay, that is if it's some fraction, 1, okay, you're going to get the vertical shrinking. Another word for that is a compression. Okay, So that is how you translate functions. We also need to talk about symmetry of graphs and graphs. So let's say we have so the word symmetry means sameness. So let's say we have this graph. It looks like so on this side of the x-axis, and it looks like so on the other side of the x-axis. Now I want these two functions to be able to lay on top of each other. And if I did that, then for any point on here, this would be my x point, and this would have to be the value of y, so I would get a point x comma y. If this graph is to lay on top of it, then the other point has to be the same exact distance in the opposite direction. So this would have to be a negative x value, but the y value would have to stay the same. If we're going to have symmetry with respect to the y-axis, okay? So this is symmetry with respect to the y-axis. And a lot of times we're just going to write symmetry with respect to y-axis, okay? So we don't want to write that out a whole bunch of different times. Okay, so what does this mean though? So for example, let's put on some points here. Let's say this is the point, I don't know, 2, 5. Then if this graph is symmetric with respect to the y-axis, it has to come the same distance across, which is -2, and then stay at the same height. So this is an example of what I'm talking about. Okay. Now remember, these are the x values, and our y-axis is actually the function values evaluated. Okay. So what we're saying here is that this is really 2, comma, the function evaluated at 2. Okay. 5 is the function evaluated at 2, that is the height. Okay. And then what we're saying here is that this is the point -2 and the function evaluated at -2. Okay, that's our y point. So what we'll notice then in the red is that f of 2 is equal to f of -2, and we just happen to know that that's 5. But this is an important part of symmetry with respect to the y-axis. Okay. So in general, what we're saying, here I have x and the function evaluated at x turns out to be y. And here I have -x, and when you evaluate the function, you get out the same value, y. So what we're saying is, when you look at the function evaluated at the negative of x, and it is equal to the function value evaluated at a positive x. Okay, so here's x is 2, here's -2. They're both the same. So if this happens, if we have that, then we have what is called an even function. Okay. So this is a test. So this is a test we'll need to put on our flashcards. Okay. So we'll know it. And we have to know that even functions are symmetric with the y-axis. Because we have other types of symmetry, okay, let's look at this function. Let's say it looks like so, and like so. So this is some y which is equal to a function, okay? Now, let's say that I would like for this graph, okay, so So let's say I have some point here, x and y, and I would like to see its reflection here across the origin. That means I would like to see negative x and negative y. So if we have that, then this is what we have as an even function, or an odd function, okay? So while I explain that, let's look here. So let's say this is the point negative 2, comma, negative 3. Let's just say on this graph. Okay. Now, then the reflection would come across here, and I would need the x values to be positive. I'm sorry, this has to be positive 2. Sorry, you guys. Positive 2, negative 3. So now I have to make the x value negative. So this would be the point negative 2. And then make the y value negative 3. Okay. So that's what I'm saying about these different types of functions. X values. And it's a little easier to see over here, like, say this was the point, I don't know, 4, comma 5, then the negative of that would need to be over here at negative 4, at negative 5. Okay, so this is what I mean by these opposite values. This is demonstrating symmetry, but this time we're talking about symmetry with respect to the origin, okay, which this is the origin. Symmetry with respect to the origin is actually 2 flips. So let's remember just a basic sketch of this. If it's symmetric with respect to the origin, if that's our original, I need to be able to do a flip over the y-axis. Okay? Well, over both axes, actually. Okay. So let's flip this thing this way. So I'm going to get this graph on this side, and then that's going to flip up. Okay, so it's going to look roughly like that. That's going over. Okay. And then I also need to go across the y-axis. And so when I'm done, after 2 flips, okay, I have the same shape that what I started with. Okay, that is symmetry with respect to the origin. And when you have this, then you have an odd function. Okay. And our test for that is if, when you take the function and evaluate it at negative x, if you get out the opposite, the negative of the original function, then odd. Okay. So this is the test that needs to go on your flashcards, and odd functions have symmetry with respect to the origin. So if you're just given a graph, you can look for the symmetries of the function and say if it's either an even or odd. Can I flip it across the y, or can I do it across the y and the x? Now, not every function is symmetric. In fact, symmetry is important and special, and only some functions get it. Okay? That's why we take the time to study them. They give us some predictability with symmetry. However, we don't always know. Okay? And it's not always easy to graph the function. So, for example, let's say our function is 4x cubed minus x. Okay. Not an easy function to quickly sketch. All right. So we want to know if this is even or odd, or if it's neither. Okay. So in that case, that is where we have to use these rules. Okay. So step 1, find f of negative x, okay? Because we want to find out what happens to the function when we put in a negative x. Okay, well, we can do that. So find f of. Okay, so f of negative x will be equal to, now the function is just 4 times something cubed minus that something. Okay. And what we're substituting in then is the negative x and the negative x. Okay. So that's substituting in. And then we need to simplify. Okay. Well, just to see this, okay, negative x cubed is negative x times negative x times negative x. Okay. And then I hope we can see here, when we subtract a negative of anything, subtracting a negative becomes positive, so we'll get a plus x. So now what's happening here, we have positive 4 negative x, so that's negative, times a negative is positive, times another negative is negative. Okay, so we'll get the negative there. And then all we can really do is x times x times x is x cubed, and 4 times that is there. So f of negative x simplifies to negative 4x cubed plus x. Now we have to compare. And we have 2 ways to compare. We have to compare to the original function and to the opposite of the original function. So our original function is just 4x cubed minus x, and the opposite of the function is negative times the original, which we can simplify. Okay. Remember, this is like negative 1, and so we can distribute this through. So minus 4x cubed plus x. Alright, so here's f of negative x. So negative 4x cubed plus x does not equal the original function. Okay. Here we have a negative, here we have a positive. Okay, they are not equal. So this means this is not an even function. Okay. Now, this is f of negative x. Okay. So negative 4x cubed plus x, we need to compare to negative f of x. And we see that it is equal to negative f of x. Okay. These are the same thing. So therefore, this is my favorite little symbol, it just means therefore, f of x is an odd function. So we do all that, so you come down here to odd, and this, when I tell you to justify your answer, this is what you'll be expected to do. Let's try another one. Let's say g of x is equal to 5x to the 4th plus 3x squared minus 2. Again, this is not a function that is easily graphed. Okay, we can't just easily sketch a graph of that. So step 1, find g of negative x. Alright, so g of x has this form. And what we're substituting in is the negative x value. And now let's try and simplify this process. Instead of writing out negative x times negative x times negative x times negative x, and here negative x times negative x, let's just think about what this should do. If I have 4 negatives, they need to become positive. And then x times x times x is x to the 4th. Okay. Plus here, if I have only 2 of them, well, the same thing's going to happen. A negative and negative will become positive. and then the x squared will stay. So now let's simplify this. 5 times a positive x to the fourth is just 5x to the fourth, plus, will stay the same, 3 and a positive becomes 3x squared minus 2. Okay. So this is g of negative x. So here we simplify. And now we're at 3, we need to compare. Compare to the original function and to the opposite of the original function. Okay. Right. So, so in this case they're g's. Right. So we see then that g of negative x is 5x to the fourth plus 3x squared minus 2. And g of x is given as 5x to the fourth plus 3x squared minus 2. And at this point, we're actually finished. Okay. These two are the same. That is, g of negative x is equal to g of x. And therefore, we can say g is an even function. And let's just build upon this from one more example. Okay. Let's say let's just make a simple one. Let's say h of x is equal to I don't know, maybe this isn't so simple. Let's say x minus 2 squared. Okay. Just to give you a hint, this will come up on your homework. We want to find h of negative x. Okay. And so what I suggest you doing is, yes, you're going to substitute this in. But I would FOIL this thing out first of all. So this is negative x minus 2 times negative x minus 2. And then go through and determine through FOILing and multiplication, do I have the original function? And so to do that, you probably want to even multiply this out. So x squared minus 4x plus 4. Compare this result to the expanded result. That will be very helpful on your homework. And let's just take one that's, let's say, I don't know, j of x was equal to the square root of x. Okay. So if we were asked to determine its even and oddness, we'd have to look at the square root of negative x. Okay. Now, this does not equal j of x, because there's a negative inside of here. And this does not equal negative square root of x, which is negative j of x. Okay. So the negative can't come outside of this square root. So in this case, if we were testing j of x equal to the square root of x, it is neither an even function nor an odd. This is neither. Okay. And we know that based upon this graph. Okay. This graph is not symmetric with the y-axis, nor is it symmetric with the origin. So you should think about symmetry and even and oddness of all of our parent functions as well. Okay. All right, I think that will do it and get you through your homework. If you have any questions, I'm here. Give me an email.